Oh, cool. Yeah, I know. Yeah, I know a few biomimickers. Okay, so we wrapped up the discussion. Let's just take a look now at the week 4 fundamentals. And I'm just going to look at this week 4 example problem. Okay, organic compound represented on 25 in the text, second figure. It is not identified in the text, but let's try to figure it out. By simply counting the atoms, we get a molecular formula of C6H10O. By examining the condensed structural and also the bond line structure, we can see that in comparing the functional group on page 20, that it's a ketone. Take note of the difference between ketones, aldehydes, and ethers. There are 6 carbons in a long chain, so it's either hexane, there's your 6, an alkane with all single bonds, hexene, an alkene with a double bonded carbon, or hexyne, an alkyne with a triple bonded carbon. The bond line structure shows a carbon-carbon double bond, which means it's a hexene. So, and the same thing is true. So A is 1, E is 2, Y is 3, and that shouldn't be all that difficult as a little mnemonic. You know, if we because it follows the alphabet. You know, A is 1, E is 2, Y is 3. Right, so you're sort of marching up the alphabet. Carbon-carbon double bond, so there's your hexene with the E. Below is another equivalent representation that basically is flipped left to right from the text image. Remember that at every angle, there's an unseen carbon atom bonded to as many hydrogens as necessary to give 4 carbon bonds. And I think we covered that when we looked at the p orbital of carbon a couple weeks ago in the dynamic periodic table. So, this is just a simple way to write it. So this carbon, the line coming out here is one of its 4 bonds, and there's hydrogen taking care of the other 3. Here's another carbon sitting right here above the oxygen. There's 1 bond, there's 2, and of course oxygen itself is a double. We saw that in the periodic table. There's another carbon sitting here, but the confusion is, oh, well, gosh, I've got 1 line coming out, 1 line coming out there. What's missing? Well, let's go ahead and just draw it. Let's just draw what's missing. So I'll just start here. So we have this, dink, dink, up, down, up, dink, dink, C, H2. And we had H3 over here, and we had oxygen. So we started with that. The question is, you know, what's actually going on at each one of these junctions? Well, that's the simple way to draw it. But if we just want to go ahead and do the whole thing, we can, you know, put a carbon here, carbon here, carbon here, carbon here, carbon here, carbon here. I mean, there are your 6, right? 1, 2, 3, 4, 5, 6. That's your hexane backbone. Where does the ane come from? Well, the double bond. Yeah. Okay, so let's just start with the backbone. Put in what we know already: single bond, single bond, single bond, single bond, double bond. So oxygen is taken care of. Single bond, single bond, single bond. So here's your hydrogen, hydrogen, hydrogen. Okay, and then hydrogen, hydrogen. Now, let's come in with a little green pen and just sort of check off what is sort of saturated and correct. So this first carbon on the left has 3 hydrogens next to it and another carbon over there, so it's done with 4. The hydrogens are easy. They each have a single bond. Check, check, check. This carbon has this 1 bond to the left, 1 to the right, 2 below. There's its 4. Oxygen has its 2. I'm going to leave the middle ones alone for now. This carbon on the very end has a double carbon bond there and a single with the hydrogen, so check. Hydrogens are done, check, check. Now, what remains are these 3 individual carbons in the middle. Let's go back to the problem statement. There was supposed to be 10 hydrogens total. How many do we have? 1, 2, 3, 4, 5. So there are 5 missing hydrogens. Let's just figure out where they go. So I'll go back to my, well, I'll just keep the green pen going now. So here's 1 for sure. Here's 2 for sure. I think I can sneak another one in there, 3. So now this carbon is saturated. This one only has 3, so let's stick another hydrogen out here. Same thing here, another hydrogen here. Yeah. So now, every single carbon has 4 bonds, and then the hydrogen is there too. So that's what we're looking at in terms of balancing that structure. Obviously, this thing I just drew at the bottom is a lot weirder and messier than the thing at the top. If we'd had all those hydrogens in that lignin, it would be even crazier. So this is kind of the standard way. It's I don't know if you heard the term Occam's razor before or not, but Occam's razor just says, make things as simple as possible, but not so simple that you start to lose information, right? So that's kind of where we're going with that.
I hadn't done it visually like this before. The only way I balanced stuff was just basically the checks and balances on the numbers.
Right. I like to start with just, what does this molecule look like, and then move to the stoichiometry.
Because that gives you an idea of actually how the bonds sit, how the structure sits, and then gives
Yep.
you kind of a more complete accounting before you just start plugging in and checking.
Yeah, and if you want, you can do a little independent research on, these are either covalent, everything along the backbone is a covalent bond. It could be that these other guys hanging out are what are known as hydrogen bonds, which are just a little bit weaker. The electron from that hydrogen is sort of, parked near the carbon, making that more negative. Well, now you've got a negative-ish carbon, and then that one proton's like, hey, I'm going to hang out near the negative to balance the charge. So, yeah. So at some level, chemistry is electrophysics.
The more I've gotten into it, the more I realize that.
Yeah. Okay. What else do we need to look at this problem before my battery conks out? Naming organic compounds can be a daunting task, but there are rules with lots of exceptions. The carbon double bond makes it the functional group. In this molecule, we usually begin specifying the location by counting from the carbon end closest to the functional group. In this case, the double bond occurs on the first carbon. So if we proceed from right to left, it's just number 1. So we're going to say this is the number 1 carbon, and it's 1 hexene. But we have another functional group. That's the oxygen. It is on the 5th carbon, so 1, 2, 3, 4, 5 to the right. Since it's a ketone, its ending is specified in table 2 as 1, pronounced one. So ketone, there's the O-N-E. So then its full name would be 1, referring to that 1 carbon, 1 hexene 5 one. And then its common name is allyl acetone. And unfortunately, that just is more or less memorization. Don't worry, I won't require you to figure out such names, but perhaps you're interested in how it's done. So I will ask you to identify the major classes identified in table 2.2. So let's just look at that. One second. I got my book for 92 cents.
Awesome.
Yeah.
Yeah, mine was super cheap. Also, Amazon's the best.
It's a great book.
There's a lot in there.
Yeah. Page 28. Okay, so here we are. I'm just going to hold up. This is page 28. So this is that's the table we're looking at. table 2.2. Just going down through here, alkanes, as we just mentioned before. So the RH, you see that? RH just means like the reactive, that's how I remember it anyway, the functional group or the reactive group. That's what the R is. And so just single carbon bonds, so carbon bonding with hydrogen, carbon bonding with carbon. That's the A that I mentioned previously. You get the double carbon bond, those are alkenes, and there are several listed. And again, you can think of those R's as just kind of bookends. You know, there's like we just saw in that lignin molecule, very top. It's going to attach to something, right? And even polypropylene, just carbon off, with a bunch of double bonds, yeah. Aromatic, that's a sometimes you think of that as benzene, but it's got basically 6 carbons in a ring. Alcohol is going to have an oxygen, an OH kind of hanging off the end. Ether is there with an oxygen sandwiched between the 2 carbons. The aldehyde has a double oxygen bond hanging off kind of at the end where there's an H. A ketone, I usually think of the ketones as like somewhere in the middle. It's like unlocking, has that double oxygen bond as well. Carboxylic acid, COOH, if you can think of a mnemonic for that. Ester, a little more complicated with a pair of oxygens, so one in the chain and another one kind of dangling off there. Amine, now we've got nitrogen in there, so that's what a lot of proteins are amino acids. So there's always a nitrogen in there, and then the amide has a oxygen double bond and a nitrogen kind of along the backbone. So good table to, and if you want, I think I see a lot of people like have flashcards. So you draw the symbol on the front and the name on the back, and you just do it like math flashcards if you want to carry it around in your back pocket, sitting on the bus, bored, waiting for the girlfriend, whatever you're doing, just bust out the flashcards. So, yeah, no, chapter 2, good stuff in here, really good stuff. All right, I think that's about all the battery I've got. I'm going to go find a charger. And I think get some sleep too. I don't know if it's a lighting.
It's been raining dark the last few days too.
Oh man, it's been a long week. Okay. Well, I think in a lot of ways we're in week 4, and it should be smoother sailing ahead in terms of lectures, homeworks, everything. Let me know if something isn't getting posted or done. Don't get mad. Just get even. Just tell. I've got a few other balls in the air. So, but this course really is fantastic. So glad we're here.
It's sort of got its like little pace to it. It just opened every week.
Yep.